Okay, hello everyone. We are going to finish up chapter 4 right now. I can't remember if we actually did this problem or not, but it won't hurt us to do it again. So in this one, we have a rescue pilot dropping a survival kit while her plane is flying at an altitude of 2,000 meters. Okay, so we know initially she is flying at 2,000 meters. She has a forward velocity, so we know it's horizontal, of 100 meters per second. We are disregarding air friction, and we want to find out how far in advance of the starving explorer's drop zone should she release the package. Okay, now we know VVI equals 0. We know that finally DF, change in vertical position, is going to be 0 because she's going to have landed. So what we're looking for ultimately is R, that we don't know. So if you look at your formula sheet, you see that R equals VH times T. Well, we know VH, but we don't know T. So with our variables that we're given, let's take a look at the formula sheet and see what formula we could use to find T. So we see we have a formula D is VVI times T plus 1/2 AV T squared. So we know VVI is 0, so this whole term is going to cancel out. So when we rewrite, we have D is 1/2 AV T squared. So we want to multiply both sides by 2 over AV. 2 over AV on this side, which will allow us to cancel the 2, cancel the AV. So that's going to give us T squared equals 2 over AV times D. Take the square root of both sides, and we will have T is the square root of 2 over AV times D. So let's put some numbers in. T is going to be the square root of 2 over negative 9.8 meters per second squared times D is going to be negative 2,000 meters. Because remember, D is the change in vertical position. So it would be DF minus DI, which would give us negative 2,000 meters. Punch that in your calculator, and you should get 20.2 seconds. So now we can go to the formula that R equals VH times T and put in our variables. So VH we're given to be 100 meters per second, and T is 20.2 seconds, which is going to give us R to be 20 meters. Okay, so this is your answer. Our next problem we want to look at, we are looking to find the velocity of an egg that is dropped off a media center as it impacts the ground. The media center is 15 meters tall. And we're also asked to find the velocity if it's thrown downward at 10 meters per second. So basically we have two parts. So let's start off and draw a little picture. Here's our media center. This would be the ground. So our egg is sitting right here. And this distance is 15 meters. Okay. We know our egg is going to fall down to the ground, so therefore we know AV or AY is going to be negative 9.8 meters per second square. We are going to assume constant acceleration, which should ring a bell and tell you that you need a kinematic equation. So go back to chapter 2 and 3 and look at your kinematic equations. And the one we're going to use is the third one, where we have Vy final squared is going to equal Vy initial squared plus 2ay delta y. So why did we choose this equation? Well, we know initially the egg is just sitting there. So we know that our Vy initial is 0. Okay? And we can calculate delta y by saying, remember, delta y is going to be y final minus y initial. So finally that egg lands up on the ground, which is 0. It started at 15 meters, so delta y is going to be negative 15 meters. So let's fill in the blanks. So Vy final squared is going to be 0 plus 2 times negative 9.8 meters per second squared times negative 15 meters. Okay, so we're going to have Vy final squared is going to be 294 meters squared per second squared. So if we take the square root of both sides, then we get Vy final will equal 17 meters per second. And that would be the answer for part A. Now for part B, we're going to throw that egg downward. So for part B, our Vy initial, instead of being 0 like it was in part A, it is now going to be negative 10 meters per second. Okay, we can still use that same third kinematic equation. So we have Vy final squared equals Vy initial squared plus 2ay delta y. So we're looking for Vy final squared. And now our initial is going to be negative 10 meters per second squared plus 2 times negative 9.8 meters per second squared, and our delta y still remains as negative 15 meters. Okay? So when we calculate Vy final squared and then take the square root of that, you should get Vy final to equal 19.9 meters per second downward. Okay, your book also talks about orbital motion, and if you look at this diagram right here on the top right, you see a little tower that has the height of h, and notice how the speed is changing. Okay, if the initial speed is small, it falls at A. If I increase the initial speed a little more, it falls at B. If I increase it a little more, it falls at C. And if I increase it even more, it goes all the way around and comes back to where it started, which is shown by D. Okay. When you have this closed trajectory, that it starts and ends from the same point, that is called an orbit. Okay. We see that closed trajectory, or that orbit, around the planets, around stars. Okay. Now notice when that initial velocity is low, though it is falling, and it falls in free fall when it does not have air resistance. So in the absence of air resistance, it's falling in free fall. Another thing we want to look at is what's called translational motion. Okay, and translational motion is motion along a path. So imagine if you throw a pencil at somebody. That pencil is going from point x1 to x2, but it also, as it's moving along that line, it's spinning or it's tumbling. Okay? So those two motions, as it's going along that path, is what we call translational motion. And you can see it illustrated in this picture with throwing a wrench. Now, if you notice in this picture all these white dots, notice how I could draw a completely straight line through those white dots. Okay? So that wrench is rotating along those white dots. That point where that white dot is what's known as the center of mass. You can find the center of mass of any object by balancing that object on your finger. For example, you could take your pencil and balance it on your finger. Where your pencil is perfectly balanced, that is what is known as the center of mass. Okay, this ends chapter 4.